In this video, you will learn about properties of exponents, including the product rule. Now let's explore how the product property works for our exponents. What we have in the first example is we have 2 to the first, so there's 1, 2, times 2 to the first, so there's 2 2's, and we can combine them, there's a total of 2 2's, so it's 2 squared. For the next one, I have 2 times 2, because there's 2's there, and then I have 2 squared again, so there's 2 2's, and then when I combine those, there's a total of 4 2's, so it's 2 to the fourth. For the next one, I have 2 to the third, so I'm going to write that out as 3 2's multiplied, and then I have 2 to the first, so I'll have 1 2, and when I combine all those together, we can see that there is a total of 4 2's, so it's 2 to the fourth. Then for the next one, I have 2 to the fourth, so I'm going to list 4 2's, and I have 2 to the second, so I'm going to list 2 2's, and then when I count, I have a total of 6 2's, so this is 2 to the sixth. And then in my last one, I have 2 to the third, so I'm going to list 3 2's, and 2 to the third, so I'm going to list 3 2's again, and when I combine those, there's a total of 6 2's. Now what's important to note is that when we're doing this, we need to figure out a relationship. But what we can see is that if I look at and I add these exponents, so if I add 2 plus 2 gives me 4. So we know this is really the result of 2 plus 2. For the next one, I can add the exponents, so the 2 and the 3 to give me 4, because we know that 3 plus 1 gives you 4. So we also have 2 to the fourth, 2 to the second, and that adds to 6. So the 4 plus 2 gives you 6. And the last one, I have 3 and 3, which gives you 6 as well. So as we can see here, there's many ways we can get these exponents, but what we had to do is just add the exponents to get our new value. So the product rule of multiplication says that for every non-zero number a with integers m and n, we have a to the m plus times a to the n equals a to the m plus n. So essentially, we're taking the exponents, the 5 and the 4, adding them to give us 9. We're taking the exponents of 2 and 9, adding them to give you 11. And this only works when the bases are the same. You're adding the exponents, but the bases have to be the same in order for this to work. Had these not both been 3's or both been h's, we wouldn't have been allowed to apply the property. Now let's look at some numeric examples of applying this property. So for the first one, I have 5 to the third times 5 to the sixth. Now we see that they both have a base of 5, so I can go ahead and just add the exponents of 3 and 6. So it becomes 5, and my exponents are 3 plus 6, and I simplify that to become 5 to the ninth. Now to simplify this, you can either plug it in the calculator, or we can think of it as multiplying 5 9 times, and when you plug that in, your answer is 1953125. But the bigger takeaway here is that we can write as either the exponent form or when you plug it in to get your answer. Now for the next example, I again see that these both have the same base. So I'm going to take my exponents and add them. So I'll have 2 to the 4 plus negative 3. And when I simplify, 4 plus negative 3 is just 1. So this is going to become 2. So my answer can be written as 2 to the first and just 2. And then for our last example, I can see that all 3 of these terms now have a base of 7, meaning that I can add the exponents for all of them. So I have negative 3, 2, and 6. So this becomes 7 and my exponent is -3 plus 2 plus 6. Now when I combine those, this becomes 7 to the 5th. So to simplify this, I can either plug it in my calculator or write it out as 7 times 7 times 7 times 7 times 7. And when you plug that in, it gives you a value of 16,807. But again, I can write it either in this form, or if I was just leaving it as my base, it would be as shown. And this gives us all of our different examples of applying these properties with numbers. Now, when variables are involved, there's a couple things you're going to do. First, you're going to group like terms that have the bases that are the same. Then you're going to add the exponents. And lastly, you're going to simplify. So for example, my terms that are just the number are 2 and 3. So I'm going to have one set of parentheses, that is 2 times 3. And then I also have the terms with the n. So I have an n to the 5th and n to the -2nd. So that's going to be n to the 5th times n to the -2nd. Now if I simplify, we know that 2 times 3 becomes just 6. And then with our exponents, we're going to add the exponents of those like bases. So it's going to become n to the 5 minus, or plus -2, however you choose to write it. And then when I finish simplifying that, that's going to become 6. And when I combine the 5 plus -2, it becomes just 6 n to the 3rd, giving us our final answer. Now let's try some examples of these. If I look at my first one, I see that I'm first going to try to combine all the terms with just the number, because I see that I have a 7. And these other terms don't have a number in front, but I'm going to assume this is really a 1 and a 1. So I can say my first set of parentheses is going to be 1 times 1 times 7. And then I have an n squared, an n to the 3rd, and an n. So if I write that as my next set of parentheses, I have n squared times n to the 3rd times n. Now when I simplify, 1 times 7 gives me a value of 7. And then for the next part, I have to add my exponents. So my exponents here are 2, 3, and while there's nothing here, we can assume that this is automatically going to have an exponent of 1. So when I combine them all together, you get n to the 2 plus 3 plus 1. And then I have to combine all of these exponents. So I get 7. And then when I add them together, I have n to the 6th as your final answer. For the next example, I'm again going to combine just the numbers by multiplying. So I have 2, 7, and 2. So I can write 2 times 7 times 2. Then I want to combine all the variables with like bases. So I'm going to combine all the ones that have y's. So I have y to the 3rd, y squared, y to the 4th. So I can write out y to the 3rd, y squared times y to the 4th. Now if I simplify the multiplying, 2 times 7 is 14, times 2 gives me 28. And I have to combine my bases by adding. So I'm going to add, so it'll be y to the 3 plus 2 plus 4. And then when I finish simplifying, the 28 stays. I add all these together to give me y to the 9th. For the next example, I'm going to again multiply the numbers together. So I have a 3, a 2. There's nothing in front of this, so I can assume it's really a 1. So I'll have 3 times 1 times 2. And then the other terms, part of the term, all have an x as the base. So I have an x to the negative 3, x to the second, and an x to the negative 2. So this becomes x to the negative 3 times x squared times x to the negative 2. Now if I multiply the numbers, 3 times 1 is 3, times 2 is 6. And then I'm going to add all the exponents for the second part of the example. So you'll have x minus 3 plus 2 minus 2. And when I simplify by combining all those together, I get this as 6. And when I add those, it's negative 3 plus 2 is negative 1, minus 2 is negative 3. So it's x and negative 3. The last thing we have to do is using our exponent rules like we learned in the last lesson, because this has a negative 3 as our exponent, what we have to do is, since this is over 1, I take this whole expression and bring it to the bottom. So it's going to become over x to the positive 3, and you're left with a 6 on top as your final answer. In our last example, we're now going to start having multiple variables. So I first want to look for all the terms that are just numbers. So I have a 7, there's nothing in front of this, so I assume it's a 1 and a 1. So when I'm multiplying the number terms, I'm going to have 1 times 7. Then I'm looking for anything that has an m. So I have an m squared and an m. So I'm only including the two m's together next. So I have m squared times m. And then the last thing is I need all the terms that have an n. So I can see that I have an n to the negative 2, and that's my only n, so this is going to be n to the negative 2. Now if I simplify, 1 times 1 times 7 is 7. For the middle part, I have to technically simplify. Since there is an exponent with the m, we can assume that that has an exponent of 1, which allows us not to write it. So I'm going to be adding my exponents. So it becomes m to the 2 plus 1. And then the n term, there's nothing else with it, so it's just n to the negative 2. Now if I continue to simplify, I can add the 2 and 1. So you have 7. 2 plus 1 gives us m to the third, and it's n to the negative 2. And then the last thing is, again, because this has a negative exponent on the n, I have to take this whole thing and bring it to the bottom because it is that negative exponent. So you'll be left with 7 m to the third all over n squared as your final answer. And this provides us with examples of different types of problems we may see. All right, now let's start going through some of the little bit more complicated examples that we may see. So the first thing I'm doing, I'm still following the same pattern. So I'm going to multiply the terms that are just numbers. So you have 4 times 2. Then I'm looking for the terms that have an a. So I have an a and a to the third. So it's a times a to the third. And then lastly, I'm looking for both of the b terms. So b squared and b to the fourth. So I can write this as b squared times b to the fourth. Now if I simplify, 4 times 2 gives me 8. For the a's, I know this is really a to the first. So I'm going to add my exponents. So it becomes a to the 1 plus 3. And then I'm also going to add my 2 and the 4 exponent for the b's. So it becomes b to the 2 plus 4. And when I simplify that, it becomes a to the 1 plus 3 is a to the fourth, and b to the 2 plus 4 is b to the sixth. There's no negative exponents. This is our final answer. In the next one, I again start by multiplying the numbers. However, none of these terms have numbers in front, so I can assume that they all just have a 1. So I can multiply the 1 times 1 times 1, and then I'm looking for the v's next, so I have a v to the negative 2, a v to the negative 4th, and a v to the 3rd. So I have v to the negative 2 times v to the 4th, negative 4th, times v to the 3rd. And then lastly, I'm looking for my u terms. I can see I have a u to the 3rd and a u to the 3rd. So it'll become u to the 3rd times u to the 3rd. Now if I simplify, I have 1 times 1 times 1, gives me a value of 1. My next part, I'm going to add the exponents for the v's. So it'll be v to the negative 2 plus negative 4 plus 3. And I'm going to add the exponents for the u's, so the two 3's. So you get u to the 3 plus 3. And then when I simplify, this stays as 1. If I combine the v's, the v, the negative 2 minus 4 plus 3, it gives me a value of v to the negative 3. And then if I combine the two 3's, that gives me a value of u to the 6. Now the last thing I have to do is I have to rewrite this. Because I have a negative exponent with the v, it has to go to the denominator. So this v to the negative 3rd is going to go to the bottom. So it's going to become 1 u to the 6th over v to the 3rd. And we know that when I have a 1 in front of a number, I really don't have to include it. So my answer is really just u to the 6th over v to the 3rd. The following examples are following the same process. However, now we have 3 variables. So if I look at the first example, I'm going to first again just look for our numbers. So the first term, there's a negative 3, and then there's just a negative, so I can assume that this is really a negative 1. So I get negative 3 times negative 1. Then for my m's, I have an m to the negative 3 and an m. So I have m to the negative 3 times n. Then for my p's, I have a p squared and a p to the 4th. So I have p squared times p to the 4th. And then lastly, for my q's, I have a q to the 4th and a term that's just q. So I have q to the 4th times q. Now for each of these, I'm going to simplify. So negative 3 times negative 1 is just 3. We know that when there isn't an exponent, this really is an m to the 1st. So I'm adding my exponents of negative 3 and 1. So it becomes m to the negative 3 plus 1. Then I'm adding my exponents of 2 and 4. So it's p to the 2 plus 4. And then lastly, again, when I don't have an exponent, I assume it's a 1. So I'm adding my exponents of 4 and 1. So I get q to the 4 plus 1. Now if I simplify, this stays as 3. The m to the negative 3 plus 1 is m to the negative 2. For the p, 2 plus 4 gives me a value of 6. And for my q, 4 plus 1 gives me a value of 5. The last thing I have to do is check for negative exponents. Because I have a negative exponent with this negative 2, it means that I'm going to have to take it and move it to the bottom. So it's going to become 3 p to the 6th q to the 5th over m squared as your final answer. For the next example, I'm going through the same process with 3 variables. So the first thing I have is I'm multiplying just the numbers. So this has a 3. The next term doesn't have a number in front, so I assume it's a 1. And I have a negative 4. So it becomes 3 times 1 times negative 4. Then I'm looking for the h's. So I have an h to the negative 1. And that's the only h I have, so it just stays as h to the negative 1. Then I want to look for my k's. So I have a k to the 3rd and a k to the 3rd. So I have k to the 3rd times k to the 3rd. And then lastly, I see that while I took care of all the variables in the first term, I still have this j squared term left. So I have to look for my j's. So I have j squared and j. So it's j squared times j. Now when I simplify, 3 times 1 times negative 4 is negative 12. H to the negative 1 can't be simplified, so it's just h to the negative 1. However, for the k's, I know I can add my exponents. So it becomes k to 3 plus 3. And then for the last one, there is an exponent with the last j, so it's j to the 1st. But again, I can add the exponents of 2 and 1. So it becomes j to the 2 plus 1. And when I simplify, the negative 12 stays, h to the negative 1 stays. I can combine the k exponents to be k to the 6th. And I can combine the j exponents to be j to the 3rd. Last thing I have to do is look for my negative exponents to bring it to the bottom, which I can see I have an h to the negative 1. So I'm going to take this and bring it down to the bottom. So it would be negative 12 k to the 6th j to the 3rd all over h to the 1st, which I can write as just being h. And again, these two give me examples where I have 3 variables. I'm just applying that process with more steps. Okay, in this last step, we're going to talk about a couple of special cases with this. If we look at the example on the left, what we have happens is if I were to go through, I'm going to combine my like terms like I have here. So negative 3 times negative 2. I have just an x and a y to the 2nd times y to the negative 2. Then I can simplify. So negative 3 times negative 2 is negative 6. The x becomes x. And 2 with negative 2 becomes 2 minus 2. Now when I go from here, we know the 2 minus 2 becomes y to the 0. The difference with this example is that we know whenever we have y to the 0 power, anything raised to 0 power is really just 1. So I can get rid of this and rewrite it as negative 6 x times 1, which we know really just becomes negative 6x as your final answer. So we end up losing the entire variable y because it has to the 0 power. In the other example, I'm going to go through and combine like terms, so don't have anything in front of u squared. So it's just negative 2 times 1. There's just a v to the 4th and just a u squared. Now if I multiply this, I get negative 2 v to the 4th u squared. There's no variables to combine, so essentially my final answer is exactly that. It's just this, which it does just kind of match what we have up here. So in certain cases, there are examples where you don't really have to simplify anything at all. So we can see with these two, these are two of our possible special cases we may encounter when dealing with our product property.